All right, everyone, welcome back. This is the last lesson, the last lecture for Chapter 2, and I'm going to do a little bit of review at the beginning of bonds, but most of what we're going to talk about here is going to be water. So remember, this is from the end of the last presentation. We have molecules, which are atoms held together in stable configuration. Compounds are molecules containing atoms of more than one element. The example that I gave you there was sodium chloride or table salt. Now, atoms are held together in a molecule by chemical bonds, and we mentioned three last time: the ionic bond, the covalent bond, and the hydrogen bond. And this will be important for you to remember and be able to distinguish between the three as we move forward. So ionic bonds occur when ions, that's the ionic part, ions are attracted to one another. So that would be like the sodium ion with its 1 plus charge and the chlorine ion with its -1 charge. Opposites attract, so they are attracted together. That's an ionic bond. Covalent bonds occur when atoms share pairs of electrons. And we'll see covalent bonds with regard to water. And hydrogen bonds occur when molecules share hydrogen atoms, and that is also important as we look at water. So ionic bonds occur when a cation is attracted to an anion. The example that I gave was sodium, the positive ion, chlorine, the negative ion, attracted together, forming the compound sodium chloride. And that's just the illustration I gave you last time of the crystalline structure of salt. Covalent bonds occur when atoms share pairs of valence electrons. So they can be shared equally, that's a nonpolar situation, or they can be shared unequally, that's a polar situation. We'll see that once again as we talk about water. Electronegativity is that ability for an atom to attract electrons. Okay, it's the affinity of an atom for an electron. It's the property by which electrons are attracted to an atom. So covalent bonds are the strongest chemical bonds. They're very hard to break. And I gave you, I mentioned the single bond, the double bond, the triple bond. And the single bond is where atoms share one pair of electrons. We have a double bond where they share 2 pairs, triple bond where they share 3 pairs. They look like this. Single covalent bond, this is hydrogen gas, 2 atoms of hydrogen. Remember, each hydrogen has 1 electron, so they share the electrons between them, right? Each energy shell, K shell, or in Clark et al., your book, they use 1n, 2n, 3, and 4n, 1n being closest to the nucleus. So the 1n shell, or the K shell, has 1 electron in each hydrogen atom. So each hydrogen atom, since K, or 1n, can take on 2 electrons, right? Each hydrogen atom has room for another electron. So between the two, they share a pair of electrons, and therefore each valence shell is full because these electrons are shared equally between the hydrogen atoms. And so each hydrogen nucleus has a full valence shell. Okay, does that make sense? Because each valence shell can have 2 electrons, and these electrons are shared equally between the two. So each valence shell, or K shell, or 1n shell, is full for each hydrogen atom. We look at the double bond. Here is oxygen gas. Oxygen double bound to another oxygen atom. So here we have oxygen with its 2, 4, 6, 8 electrons, right? But remember, 2 are in the first shell, the K shell or the 1N shell, and then we have 6 in the outer shell. Remember that the outer shell can hold a maximum of 8. We have 6 there in a normal high oxygen atom, so we have room for 2 more. Likewise, you have an oxygen over here with its 6 valence electrons, so it has room for 2 more. And so by sharing 2 pairs, the valence shell or the outer shell or the L shell or the 2N shell, whichever term you want to use here, for each oxygen atom is full. Each one contains 8 electrons because these 2 pairs or 4 electrons are shared equally. Triple bond, we have nitrogen bound to nitrogen, and we have 3 pairs being shared equally between the 2 nitrogens. All right, that's 2, 4, 6, and 8. So each valence shell or outer shell for each nitrogen atom is full. See how that works? And so that's a triple bond, sharing 3 pairs of valence electrons. Okay, so we want to talk about water now, and this little illustration simply shows you how important water is to living systems, to organic systems. Now here we see humans here, and look, you can compare the two. Look at the baby here, newborn infant, 75 to 80%, the weight of that infant is water weight, 75 to 80%. For the average adult male, it's in upwards of 60%. So it's still more than 50% of your weight is water, or your mass, I should say, is water. And for the adult female, upwards of 55, it's 50 to 55%. So we still have at least 50% of your mass, if you're an adult female, is water. So that's how important water is to organic systems or living systems. So let's look at water. My slide here is titled Water, Water Everywhere, because water, it's one of the most abundant molecules in the atmosphere. So water, water everywhere, right? So a water molecule looks like this. It's composed of, and you're familiar with H2O, like everybody knows H2O, but do you really know what that means? Well, here's what that means. You have this big oxygen atom, and you may recall that an oxygen ion has a net negative charge, or I should say the electronegativity of oxygen, okay, its affinity for electrons is strong versus the electronegativity of hydrogens, okay? So what happens here, the hydrogens in this arrangement, hydrogens have a net positive charge. Because remember, they have no electrons. They only have 1 proton. They have 1 positive charge. So they have a net positive charge. Hydrogen here has a net positive charge again. And this oxygen can then take on 2 additional electrons. Okay, so hydrogen has 1 proton, 1 electron as a net negative charge. It's interesting to me, but I don't want it to be confusing to you. Hydrogen can either act as a positive charge or a negative charge, and we'll see this later on in cellular respiration as we look at the electron transport chain. So hydrogen can either donate a proton on one hand or an electron on the other hand, because it has 1 of each. Okay, that'll be more clear as we get later on into biochemistry and cellular respiration. But in this arrangement, hydrogen has a net positive charge, hydrogen has a net positive charge. This very big, hefty, large oxygen atom has a net negative charge. Okay, So opposites attract, negative is attracted to the positive, likewise over here, but you really do, subatomically, you really do have an angle here, because look, this is positive and this is positive, so these guys are not attracted to each other. So that's why these bonds are not straight down, because these hydrogens want to repel each other because they both have the same charge, a net positive charge. And so that's why we see the angle here. And there really is, subatomically, there really is an angle there. Okay, so keep that in mind. So as we look at water, just a bunch of water in general. So we have, right, just a bunch of water molecules. That's all water is, a bunch of water molecules. But look, water molecules, when they're all put together, do not just end up random like this. Because water is a polar molecule, I said before, the oxygen has a net negative charge and each hydrogen yields a net positive charge. And so thinking about it, or looking at this diagram, it should maybe, you should get the idea, or at least appreciate it from this illustration, that just as these hydrogens repel each other, so do hydrogens on adjacent water molecules repel each other. However, do you think that maybe this oxygen could also be attracted to that hydrogen? And in fact, that's exactly what water molecules do. The oxygen of one water molecule gets attracted to the hydrogens of two other water molecules, and it looks something like this. There's your oxygen, net negative, and your hydrogens, net positive, with their little angle there. But look, another oxygen with its net negative charge gets attracted to the net positive charge of an adjacent water molecule. And likewise, we have the same thing going on over here. The bonds between oxygen and hydrogen of one water molecule are covalent bonds. These are covalent bonds. But the attraction between an oxygen of one molecule and a hydrogen of another molecule is a very weak attraction. We call that a hydrogen bond. And that's one of the weakest chemical bonds that we see in nature. Right? A very weak bond, very easy to break. You know, it's not that hard to boil water. But you'll notice here that this oxygen has two hydrogens, and so as a result, two different oxygen molecules can be attracted to this water molecule. Or I should say, two different water molecules can be attracted to this water molecule by way of hydrogen bonds between adjacent water molecules. And if we add a fourth one, can you guess where it might go? Where it might fit in this arrangement? Right there. And so we get this nice little sort of geometric pattern going on between water molecules. And then you're going to have another oxygen come in here, hydrogen bond there, another oxygen come in here, hydrogen bond there, and it's just going to get bigger and bigger and grow, and then you have water everywhere. Liquid water everywhere. So water is a fantastic, it is, again, one of the most abundant molecules in the atmosphere, but water is wonderful in so many different ways. And so we're going to look at some of the properties of water here. This is just another way of looking at H2O. This little delta plus and delta minus here just demonstrates for you the net negative charge here, net positives over here. All right, so the electronegativity of water, there's that word electronegativity. It's the ability for an atom to attract electrons. So oxygen, which has an atomic mass of 8, attracts electrons more strongly than hydrogen, which has an atomic mass of 1. All right, so by virtue of oxygen's electronegativity, hydrogen, or two hydrogens rather, get attracted to the one oxygen molecule by way of their oxygen has a larger electronegativity than does hydrogen, and so they are attracted by way of their electronegative potentials. As a result, because remember I said that hydrogen has one proton and one electron, so as a result you get a net positive charge out here. Don't let that be confusing. It's the electronegativity of oxygen that attracts the hydrogens, the electrons and hydrogens. But once they combine and form that molecule, then you get the polarity coming into play, with oxygen being net negative, each hydrogen being net positive. All right. Okay, so the wonders of water continue. Water forms hydrogen bonds, as we have seen. Hydrogen bond forms when a hydrogen atom covalently bonded to one electronegative atom like oxygen, also attracted to another electronegative atom. And you'll remember the little illustration that I showed you before, where you have one water molecule attracted to another water molecule by way of the hydrogen bonding between the oxygen of one and the hydrogen of the other. So in living cells, the electronegative partners are usually oxygen or nitrogen. So here we see once again water, right, with its differential charges, positive, positive, negative there. Look at ammonia here. Ammonia is a nitrogen atom bonded to 3 hydrogens. Okay, and so these are going to be covalent bonds between the nitrogen and the hydrogens. Same situation, we have a net negative here and a net positive down here, so we have a polar situation here. But look, the net negative of the nitrogen can be attracted to the net positive of the hydrogen on this water molecule. And so you get ammonia bonding to water. All right. Okay, so in larger molecules that we're going to be looking at, we call them organic molecules because the base structure of them is carbon and hydrogen. These little dark little spheres here, little balls, represent carbon. And there you see a water molecule. And so this a hydronium molecule, that's an oxygen and one hydrogen. But remember that you can have this net negative charge is going to be attracted to the net positive on this carbon. Carbon, by the way, can entertain 4 single bonds. All right, and so you see it here. In this case, on the end, this carbon is bound to 1, 2, 3 hydrogens and another carbon, so that's 4 bonds. This carbon is bound to 1, 2 hydrogens, 1 carbon here, 1 carbon there. That's its 4 single bonds, single covalent bonds. This carbon is bound to 1, 2 hydrogens, covalently bound to another carbon, and covalently bound to this oxygen of this OH molecule. Okay. Okay, so we have a couple of properties of water to remember. One is cohesion, and I have this illustration here of this little water skipper or water skimmer or whatever you want to call it. I don't know what this little insect is. I don't know what its scientific name is, but little Jesus bug that walks on the surface of the water. The property of water that allows this insect to do such a feat, to carry out such a feat, is cohesion. Cohesion is where water molecules stick to other water molecules. Via hydrogen bonding, as we've seen, water is very sticky. If you, you can do this at home. You can take a plate, take a paper plate or a styrofoam plate, and put some water on the table, and then lay the plate bottom down on top of the water. And then try and blow the plate. Just blow it with your, just blow on it. And see if the plate will move. It will not move. Now, if you did that without the water, the plate would just scurry across the tabletop. But water is sticky like that. It sticks to itself by way of those hydrogen bonds. And so when you get a layer of water between the plate and the tabletop, the water is sticking together, it essentially glues the plate to the tabletop. Okay, that's cohesion. Now, on the other hand, you have adhesion, where water molecules stick to other polar molecules via hydrogen bonding. This, it's kind of hard to see, but here's a beaker of water, and these are little capillary tubes of different sizes. And when you take a little, it's just an open-ended glass tube, and you put it down into this beaker of water, without doing anything, water will start climbing up the capillary tube. And it's, maybe you've had this done at the doctor's office, where they take a sample of blood and they puncture your finger, do a little finger stick, and they take a little glass tube and they touch it to the blood, because blood is an aqueous solution. It starts climbing up the tube. That's adhesion. That's the property of adhesion that causes it to do that. You'll notice the more narrow the tube, the thinner the tube, the faster the water climbs up. Okay, that's the property of adhesion that allows the water to climb up a tube, or that allows your blood to climb into that little glass tube at the clinic. Okay. So we have a couple of different bonds, and I've already mentioned this, so I'm just going to be brief here. The bonds of water, we have covalent bonds between oxygens and their associated hydrogens, and then we have hydrogen, oh, by the way, polar covalent bonds, because remember, water is a polar molecule with its net negative charge here and its net positive charges here. All right, so that gives it essentially two poles. That's why you call it polar. It has a negative pole, kind of like the battery, right? It has a negative pole and a positive pole. So we call it a polar molecule. That's where that term comes from. And then you have hydrogen bonds, very weak bonds, between the oxygen of one molecule of water and the adjacent, the hydrogens of an adjacent water molecule. Okay. So we have those two different bonds going on in water, in a molecule of water. So hydrogen shell is the sphere of water molecules that form around particles of solute. Now what we know here is that water, we call it the universal solvent, S-O-L-V-E-N-T, solvent, because lots of things, many things can dissolve in water. Not just sugar and salt. Many things can dissolve in water. That makes it a solvent. And what happens is when particles, in fact they're showing sodium chloride, table salt right here. You throw some salt into a glass of water, and what happens is the sodium and the chloride of the salt crystals dissociate. They come apart, and they are otherwise attracted to the water molecules. Sodium being positive gets attracted to the negative oxygen pole of the water molecules. Chlorine, with its negative charge, remember chlorine, we have a chlorine ion here, an anion, negative charge, is attracted to the positive ends of these water molecules, the hydrogen ends of these water molecules, right? And so what happens is around each of these sodium ions and these chlorine ions, you get this little sphere of water molecules forming around it. And that's called the hydration shell. Hydration referring to water. And it's called a shell, don't think about it as a hard, tough shell. But anyway, it's just a series of water molecules surrounding each ion due to the differentials in electrical charges. Right? It's called hydration shell. So now we have two terms to remember: hydrophilic and hydrophobic. If you are an arachnophobe, if you are an arachnophobe, right, you are afraid of what? Spiders. Phobe comes from phobic or phobia. You know what a phobia is? It means when you're afraid of something, right? You have a fear of something. So hydro pertains to water. So hydrophobic means literally fearing water, or in this case, hating water, or the tendency for a molecule or an ion or a substance to not mix well with water, to repel water. Great examples are oil, car wax. You wax your car, right, and it rains and the water just beads up and rolls off, right? Because car wax is hydrophobic. Likewise, when you mix oil and vinegar to put on your salad, vinegar is an aqueous solution. It's a water-based solution. When you put the oil in there and you just sit it on the table or just put it in your refrigerator, right? When you take it out to use it to put it on your salad, the oil and the water have separated because oil is hydrophobic. In order to use it properly, you shake the bottle up, you mix it together, and then you pour it on your salad, and you get the combination. And it doesn't really physically mix, but it disperses together to give you the oil and vinegar salad dressing. Okay, on the other side of the coin is hydrophilic. Phil or phile has to do with love. So hydrophilic means water-loving, or water attracting, is the ability to mix or dissolve with water, or mix with or dissolve in water. So these are things that easily dissolve in water. Hydrophobic are things that do not dissolve in water. Things that dissolve easily in water, good examples are sugar and salt, right? You take a glass of water, you throw some sugar in there. You take a glass of tea, which is an aqueous solution, right? Unsweetened tea. You throw some sugar in there, you stir it around, the sugar dissolves, and you have sweetened tea. All right, so in the case of chlorine being negative, it's hydrophobic. And here we have a hydrophilic sodium. That's not really a good example here, really, but it's the combination of sodium chloride that's hydrophilic. All right, so remember those terms: hydrophilic, water-loving; hydrophobic, water-hating, because we'll bring those back into play when we talk about the cell membrane. Some wonderful properties of water. Water has a high specific heat, so it takes a large amount of heat to change the temperature of water. In other words, 100 degrees Celsius to change the temperature of water, right, to boil water. 212 degrees Fahrenheit, that's pretty high, right? We have other things that it doesn't take as much heat to change the temperature of water. Water has a high, so remember that, it has a high specific heat. In other words, it takes a lot of heat to change the temperature of water. Water has a high heat of vaporization. So the energy required to change liquid water to vapor, in other words, to boil water, right, it's high. Evaporation of water from a surface causes cooling, when you're outside in the summertime and you're exercising, you sweat. That's the cooling process. That's um, vaporization of water from your body. It takes a high temperature to do that, and that's how your body keeps itself cool, because if your body allowed you to get up to the high temperature, then you would just combust. You would spontaneously combust. All right, but high heat of vaporization, in other words, takes a lot of energy to vaporize water. Solid water is less dense than liquid water. So in other words, ice, frozen water, ice, solid water, less dense than liquid water, and that's why ice floats on water. You put your ice in the glass, you pour your sweet tea on top, and the ice floats to the top, because ice is less dense than liquid water. And so that's why water freezes from the top down. That's why when you, in the winter time, right, people that do ice fishing do not go out as soon as the pond freezes over, because water freezes from the top down. So as soon as you see a layer of ice on top, that doesn't mean that's not very safe. That's very thin ice. So you have to wait for a while until that water freezes down to 6 inches thick, or whatever it is, however thick it is, when they can walk out onto it. Or for some people, in some situations, ice road truckers, right? They drive trucks on top of the ice. All right. Because ice freezes from the top down, so it gets very thick that way, and it's still liquid underneath. And so this is an illustration showing you the three physical states of water, and here you see ice. So look at the very geometrical arrangement of these water molecules in ice versus this is liquid water. And here you just have a bunch of random water molecules all over the place, and they're, hydrogen bonding to one another. But look, this thing is very geometric, very solid, if you will, and because of this solid structure, you cannot get any more water molecules into this thing, right? These are like little walls built up. You cannot get more water into it. You can't make this thing bigger. You can add additional water molecules out here as the water continues to freeze. But in this single structure, you cannot get more water into it, right? So it is as dense as it's going to be. However, in the same amount of space, you can pile in more water molecules, therefore making liquid water more dense than solid water. And that's why ice floats. Steam over here, the water molecules just dissipate. They come apart because of the high heat. The hydrogen bonds are broken, and the little water molecules just fade into the atmosphere as vapor. That's steam. All right, more properties of water. Water is the universal solvent, as I have said. Water dissolves in many things. Polar molecules, also ions like sodium and chloride. Water organizes non-polar molecules. It's the hydrophobic and hydrophilic and hydrophobic properties of non-polar molecules that allow water to arrange them. It doesn't make any sense now, but we'll see that when we talk about the cell membrane. And water itself can form ions. Water itself can form ions, right? You can have, remember, water is H2O, so you can have one of those hydrogens dissociate from the other, from the oxygen molecule, and so that you have a free floating or freestanding hydrogen ion and an O and an H, which we call hydroxyl ion. Its negative charge, net negative charge, because oxygen is bigger than hydrogen, and then you have that little hydrogen over here with its net positive charge, right? So we have a hydrogen ion and a hydroxyl ion or hydronium ion, And that's how you make acids and bases. And that's the essence or the basis of pH, which we'll talk about. That's how acidic or how basic any substance is. All right, and we'll talk more about pH in the next chapter. All right, so that's the end of chapter 2 for you. That allows you to go forth and complete the quiz on chapter 2, and I will see you in chapter 3.